I am an architect leading an autonomous driving project. Our collection vehicles collect a large amount of data from streets and alleys every day. Each collection vehicle generates about 3 terabytes of data per day. 20 vehicles means 60 terabytes. If the fleet expands to 100 vehicles, the data volume will reach 300 terabytes per day. How can such massive data be stored and managed? Object storage is almost the only choice. It not only has a clear cost advantage, but also allows for flexible and efficient expansion. However, storing the data isn't the end of the story, because the total bandwidth requirement at this point could reach hundreds of gigabytes per second. While common object storage services often limit throughput to dozens of gigabytes per second, the data loading efficiency is far behind the processing speed of GPUs. This leads to computing resources always being idle, not only slowing down the training progress, but also wasting resources. On the basis of using object storage to save costs, how can we simultaneously reduce latency and improve system throughput? My answer is JuiceFS. It perfectly combines object storage and distributed file systems. Through data and metadata separation and a multi-level cache architecture, JuiceFS can effectively improve access efficiency, making data reading and writing faster. No need to worry about object storage throughput limits. To understand how JuiceFS achieves all this, let's start with the most basic, local caching. As everyone knows, reading from a local disk is much faster than reading from remote object storage. Reading data locally allows GPU nodes to avoid waiting long for remote storage responses, maximizing the use of computing resources. However, in scenarios like autonomous driving, the amount of data collected is enormous. Trying to put all of it on a single local computing node is obviously very difficult. At this time, JuiceFS's distributed cache comes in handy. It expands the cache pool from a single node to the entire cluster, where all nodes share cached data. Suppose each node has a cache capacity of 10 terabytes, and the entire cluster consists of 100 storage nodes. That provides 1,000 terabytes of total cache capacity. Each node caches a portion of data to avoid the waste of duplicate storage and improve cache resource utilization and response speed. JuiceFS uses a consistent hashing algorithm to reasonably distribute cached data across multiple nodes. Each node has its own responsibility and works together. As the number of nodes increases, capacity and throughput can be easily scaled. When running multiple training rounds, nodes retrieve data locally from the cache, no longer needing to wait for remote object storage to slowly return data every time. Training efficiency is maximized. With the help of caching, reading performance has been significantly improved. However, write operations still cannot break through the performance bottleneck of object storage. Due to the immutable nature of object storage, every modification requires rewriting the entire file. That is to say, for a 100 gigabytes file, even if you only want to append a few hundred KBs of new data, the entire file must be re-uploaded. This is obviously very inefficient. So, how can we make write operations more efficient while ensuring performance? The answer is data chunking. JuiceFS does not store files as a whole, but splits them into a 3-layer structure: chunk, slice, and block. First is the chunk, which is a logical partition of the file, fixed at 64 MB in size. JuiceFS splits large files into multiple chunks, so the system can quickly locate the specific part of the data you want to access. Next is the slice. A slice represents a single continuous write operation. JuiceFS does not modify the original content, but generates a new slice to record the written data and its position in the file. Each write is incremental, requiring no changes to existing data. Finally, the block. The block is the actual data unit stored in object storage, each 4 megabytes in size. When writing, a slice splits data into multiple 4 megabytes blocks. These blocks can be uploaded or read independently. Multiple blocks can be processed in parallel to fully utilize network bandwidth, thereby significantly improving performance. By using chunks to locate, slices to track writes, and parallel block storage. This three-layer design enables JuiceFS to achieve efficient file reading and writing. Here comes another question. Since files are split into so many small pieces, the complexity of the entire system increases significantly. How does the system know which blocks correspond to a specific file, and ensure they aren't corrupted after reading or writing? The answer is the metadata service. The metadata engine is like the brain of the file system, allowing the system to accurately identify which file each block of data belongs to, and reassemble them in the correct order. It depicts the hierarchical relationship between files, ensuring that every block of data in object storage can find its place. JuiceFS adopts a strategy of separating data and metadata, storing all metadata in an external database. This enables the system to leverage the high availability and transaction mechanisms of the database to ensure reliable storage and efficient access to metadata. JuiceFS supports various databases as metadata engines to meet the needs of different scales and scenarios, including traditional SQL databases and high-performance KV stores. When dealing with ultra-large-scale data, especially with tens of billions or even hundreds of billions of files, you can choose to use KV stores such as TiKV or FoundationDB. Their distributed architecture uses horizontal sharding to distribute data across multiple nodes. Each data shard has multiple replicas to ensure high availability and fault tolerance. However, the flat structure of KV storage sometimes requires operations on each key value pair across nodes when processing metadata operations, which results in some network overload and complex consistency issues. Another option suitable for hundreds of billions of scale is the metadata engine developed by JuiceFS. It adopts a directory tree structure, naturally supports the hierarchical structure of files and directories, and efficiently manages hundreds of billions of files through partition design. As the storage scale increases, the directory tree structure of JuiceFS supports subtree splitting, distributing subdirectories across different metadata servers to further achieve horizontal scaling, ensuring that even at the scale of 100 billion files, the system can still maintain high performance and operational atomicity. So far, we have introduced the core architecture of JuiceFS. The metadata engine manages the organizational structure of files. Object storage saves the actual data. The sharding mechanism improves reading and writing efficiency, and the caching mechanism reduces access latency. These components form the underlying capabilities of JuiceFS. But in order to provide these capabilities to users and allow applications to access JuiceFS like a local disk, another key player is needed: the client. The JuiceFS client is the bridge connecting the business and the underlying storage. Its core capability is to implement full POSIX semantic support through the Fuse user space file system. POSIX is a set of file operation standards defined by operating systems, including reads or writes, permissions, timestamps, file locks, memory mapping, etc. These standards allow you to mount JuiceFS locally and operate directly using commands such as ls and cp. Without any modifications, applications can read and write data as if they were accessing a local disk. Besides POSIX mounting, JuiceFS also provides multiple access methods: Python SDK, Windows Client, Hadoop Java SDK, Kubernetes CSI driver, and S3 gateway. These cover various use cases, whether in serverless environments, restricted containers, or applications requiring S3 API compatibility. All can connect to JuiceFS. In summary, the core goal of JuiceFS is very clear: to build a high-performance, low-latency storage system for massive data, allowing business nodes to access underlying storage efficiently, conveniently, and securely, while fully retaining the operational semantics of the file system. Now, JuiceFS supports our autonomous driving platform. Every day, hundreds of terabytes of sensor data collected by our vehicles, and thousands of concurrent training tasks are all running steadily and continuously. If you are facing similar challenges, whether in autonomous driving, generative AI, quantitative analysis, model training, and inference, feel free to leave a comment and share your experience. If you found this video helpful, please share it with your friends. Thanks for watching. Goodbye.